Okay, hi everyone. This is the first lecture of CHEN 422 Chemical Reaction Engineering. Um, so this is week number 1, and the schedule for this week will be just a course introduction, and then we'll talk about kinetics of homogeneous reactions. Also, homework 1 has been assigned for this week. Homework 1 has been posted on Blackboard, and it will be due next Tuesday. Okay. And again, similar to senior design for this course, the schedule has been posted. So if you have any questions or any doubts about the pace of the course or when our homework's due, and when our exams due, and things like that, just always look at the schedule and follow it. We'll be sticking to it throughout this semester. Okay, so again, my name is Omar Basha. I'll be your instructor for this course. This is my email here. If you have any questions, you want to reach out, ask anything, any doubts, just please go ahead and do so. The graduate assistant for this course will be Mr. Shemeka. He's one of my graduate students. He knows a lot of this chemical reaction engineering material, and he's a very good resource. So please reach out to him if you have any questions. He should also be sending out his office hours within the next few days. With regards to my office hours, I'm available all day Thursday, so I'm freeing up Thursday. If you have any questions, I'll be there. And if Thursday doesn't work for you, just send me an email. Let's make an appointment, and we can sit down and discuss the material or any other questions you have. Okay, lectures will be pre-recorded as well as homework solutions and will be made available on Blackboard every week at 8 a.m. PDF slides of lectures and reading materials will also be posted. So the PDF slides should be sufficient for your studying and progress in this course. However, if you're looking for additional material, the 2 books I'm using are Elements of Chemical Reaction Engineering. I'm using this book primarily for the polymath software or the polymath portion of the course, which we will come up to in a couple of weeks or so. And however, primarily this course will be following the book by Octave Levenspiel, Chemical Reaction Engineering. This is a very good book. It's a very good resource to have. It's it's very well written, very easy to read, and if you can get your hands on a copy or downloads of the internet, I highly recommend that you do so. Okay, prerequisites for this course: heat transfer, thermodynamics, organic chemistry. You're expected to know elements of each of these topics, throughout this course. So it's just for your information. And the grading of this course will be equally divided between homework, exam 1, exam 2, and final exam. Okay, your exams, the way I give exams is that you'll usually get 4 or 5 problems. If you're given 5 problems, for example, 4 of them will be very similar to the homework, and then you'll get an additional problem, which would be new or maybe somewhat different, and test basically your knowledge of the material. The exam dates for exam 1 and exam 2 have been set for September 29th and November 3rd. So please plan your schedules accordingly. I don't think we will be changing these dates, whether for this course or for process design. So just giving you a heads up, plan ahead for these dates. So let's jump into the course, just with a smooth type of introduction here. So what's chemical reaction engineering really? It's the heart of what chemical engineers do, right? So if you think about civil engineering, for example, they do construction. Mechanical engineering, they do machinery, moving parts, all this stuff. Electrical, electronics, lights, bulbs, wires, whatever. Chemical engineers, we change materials from the raw form basically to their final usable form, right? And we design systems, factories, plants in which chemicals, biochemicals, foodstuff, medicine, whatever it is, are purified, separated, reacted into constituent parts, and their final um, basically form for consumption and for use by the public and the economy. And chemical reaction engineering is primarily concerned with sizing, predicting the performance, and designing equipment in which reactions occur, right? And the equipment could be simple as a batch reactor, which is like your cooking pot, right? Or it could be very complex where you have moving elements, you have fluidized elements, you have other types of things. And we really, in chemical reaction engineering, we're trying to answer the following types of questions. So what kinetic descriptions can be derived from experimental observations? How do we specify the reactor type based on feed conditions and kinetics? And if we know all of this information, what will the product look like? Well, how pure will it be? What will be the conversion, all this stuff? How big should the reactor be to produce a certain amount of product? If I have multiple reactions, what will be the conversion of the feed, yield of the product, all this stuff. And then we go on to answer also design questions such as, what type of reactor do I need? Do I need multiple reactors? If I need multiple reactors, will they be in series? Will they be in parallel? Will I have a recycle? All of this stuff. These types of generalized design questions. And then we also have unit optimization questions, such as what fluid contacting pattern should be chosen to maximize the amount of product made. Sometimes it could be as simple as using a distributor which generates larger bubbles, or using a catalyst with a smaller particle diameter, which just affects the way mass transfer happens, affects the way the fluid dynamics happen, and this optimizes the design of your reactor and eventually your overall plant. And also from chemical reaction engineering from this course, you should try to get an intuition of, if I do an experiment at a very small scale, will this scale up reasonably well? Will the results I see in a lab be easily translated to a large plant, or what adjustments, what corrections would you need to put in place to make it happen? And your chemical process usually looks like this. Almost all chemical processes look like this, right? Where you have three main steps. You have a feed or raw material coming in. They undergo a feed preparation step right here, which usually involves some types of physical treatment to prepare them for chemical reaction. And the pre-treatment steps usually involves some sort of physical type of um, operations, such as crushing, grinding, dissolving. If, for example, if you have coal, if you have natural gas, you want to do some desulfurization, maybe dehydration, whatever it is. It's just a preparation process. It's a physical process. After you've cleaned up your raw material, prepared it for the reactor, you put it into the reactor, where you have the reaction, right? Where it changes from one molecule to the other, and you're transforming this material towards a desirable product. And then after the reactor, you usually have another step of physical treatment. However, in this case, this is more of a thermodynamic treatment where you have either distillation, evaporation, filtration, absorption, whatever it is, to try and enhance the purity, remove any junk you have, try to recycle some of the feed, all of this stuff, and also minimize waste, minimize energy losses, all of this stuff. So the first and last steps, usually deal with them in your separations class, in your heat transfer class, as well as in process design. In this course, we will only focus on the middle step, which is the reactor, right? We assume the feed comes in clean, pre-treated, and everything's done for it. And once we generate the product, we don't worry about it. This is for other courses. Okay. And before moving on, let me define a very important term which will be present throughout the semester. This is called the performance equation. Okay, because in reaction engineering, there are four pieces of information which you will see all the time or which you will have to deal with all the time. First one is the kinetics, right? And by kinetics, I mean the chemistry of it, the reaction which will happen whether you do it in 1 microliter or 10,000 barrels a day. The chemistry will still happen. The molecules will still, once you get them together, they'll react the same way. So first one thing is kinetics. Second thing is the feed or start conditions. How pure is your heat coming in? What's its temperature? What's its pressure? What's its concentration? These are also important pieces of information. Third thing is the reactor size. Am I doing this in one very large reactor, two small reactors in parallel, maybe one large reactor, but it's a very long tube? What does the reactor look like? And this will affect things such as your contact time with the catalyst, how much heat transfer is happening, how much mass transfer is happening, all of this stuff. And then finally, your outlet or final conditions, which is if I put it through this reactor under these conditions, what will my product look like? Will it be just 100% nice, cute, clean product, or will I have a lot of junk in it, a lot of maybe unreacted feed in it, maybe a lot of undesired products, whatever it is. And in order to link all of these four pieces of information, we derive something called the performance equation, okay? And the performance equation will enable us to answer any question we have about the reactor, about the system, okay? And we will derive performance equations for different types of reactors as we move throughout the course, but this just to give you a heads up so that you understand what this means. And once we derive a performance equation for a reactor, if I have three of these, I can always extract the fourth, right? So if I have the feed conditions, reactor size, outlet conditions, I can know the kinetics. If I have 1, 2, and 3, I can know 4. If I have this, if I have any three of them, I can always get the fourth one. And your performance equation, again, just be prepared that it can be an algebraic form if you have a simple system, or it could be a partial differential equation if you have a more complex system. And if you have a performance equation, which is a differential equation or a partial differential equation, we will need to use some sort of software to solve it. And in this course, we will be using Polymath. So, I mentioned Polymath earlier, and this is what Polymath is. It's basically a simple package which will help you solve differential equations or partial differential equations for reactors. Good. The next couple of slides have just some nomenclature for you guys. So if there's any units which you're not sure what they represent, any letters you don't know what they mean, just look back at these slides for your nomenclature, and it will just for your reference, basically. It also involves, some of the abbreviations we'll be using. So IBR is ideal batch reactor, CSTR is the ideal continuous stirred tank reactor, and PFR is a plug flow reactor or ideal plug flow reactor. Okay, so just have a look at them and make sure you're aware of what they mean. Okay, so let's move in and talk about the rate of reaction. So the rate of reaction is basically the speed, because you have rate at which the moles of a component gets consumed or formed, right? And the rate of reaction is usually represented using the letter R. Let me see if this will work. Rate of reaction is usually represented using the letter R. So this is your rate. I here corresponds to your component. So for example, if I have a CO2 being reacted, or let's say carbon monoxide being reacted, I'll write it as RCO. And then your rate of reaction usually represents DNI, which is the rate of change of number of moles of component I per time, right? So because it's a rate, you always have time. So dNi by dt will always be present, right? So it's the change of number of moles per time. However, this also, in addition to dNi by dt, we usually try to present the rate of reaction in terms of some other type of space parameter, okay? Some other type of space parameter. So in this case, I have volume. In other cases, you have other parameters. So your rate of reaction is 1 over V multiplied by dNi by dt, and this is moles of I formed per time per volume of fluid, right? And this is the reaction rate based on unit volume of the reacting fluid. We can also represent the rate of reaction in terms of other volumes or other mass, other mass parameters within your reactor. So for example, I could represent it as based on unit mass of solid in a fluid solid system. So in this case, my reaction rate will be Ri, and the typical convention is to use 1, basically, comma at the top here, 1 over W multiplied by dNi by dt, where W is the mass of the solid. Alternatively, you have 1 over S multiplied by dNi by dt. S is your interfacial area, and in this case, your reaction rate is based on the interfacial area between phases. You could have it in terms of volume of solid, so based on unit volume of solid in gas-solid systems, or you could have it in terms of volume of reactor, based on unit volume of reactor in in your system. However, in all these cases, you can see that, you know, dNi by dt is always there, right? So I need to get used to this drawing thing, right? dNi by dt is always there. So change of number of moles per time is always there when representing the reaction rate. And then we usually add another element, which could be a volume of fluid, could be mass of solid, could be interfacial area, volume of solid, or volume of reactor, to try and represent this change of moles per time, and then per either a volume or a mass component as well. And as you can see, they're all related, right? Because they all have this dNi by dt. So if I can always relate any of these two reaction rates, right? And this is what's shown on this slide. So dNi by dt is equal to V Ri W Ri prime S Ri double prime Vs triple Ri triple prime, and then Vr Ri quadruple prime. And checking how the rates has been defined is important when deriving your performance equation, because, you know, you could have some sort of kinetic expression, which someone did experiments and he got his reaction rates in terms of the mass of the catalyst, for example, but you're interested in determining the reactor volume. So you have to do a conversion to change from mass of catalyst to volume of reactor, whatever it is. And it's important to realize that they're all related using this expression. So they're all related using the basic expression here, which is change in number of moles per time. Good. Moving on, talking about reactions. So reactions happen. There are all types of reactions out there. They happen at all types of speeds. So, you know, this figure is taken from Levenspiel. You can see that some reaction rates are extremely slow. So, and this scale shows the rate of reaction, which is moles of A reacting per meter cubed second. And you can see that, for example, for an industrial wastewater treatment plant, very slow. It's on the order of days where you get the water, you throw it in a very large basin, and you keep it there for a few days for, for all your biochemical reactions to occur, and then before moving it on to the next step. So in this case, the reaction rate is very slow. In other cases, so for example, in catalytic reactions in oil and gas or in polymerization, the reaction rate is less than a second, right? So you have a big reactor, but you want the reaction to occur in 1 second. In oil and gas, for example, or in a coal furnace, you want the reaction to happen quickly. In rocket engines, for example, you want the reaction to happen even more quickly, on the order of milliseconds or whatever it is. And then you have biomolecular reactions, you want them to happen almost immediately, right? Almost instantaneously. So you just need to realize that, reaction rates can span over a very wide range, okay? But you need to have a sense of what's going on. So if you're dealing with the wastewater plant and you get a very high reaction rate, something's off. Designing a jet engine, very low reaction rate, something's off. So try to have a feel, link the application to the numbers you're seeing. Okay, let's have a look at a quick example. This is example 1.2 from Levenspiel. And in this example, he says, a human being who's 75 kilograms consumes 6,000 kilojoules of food per day. You're told to assume that the food is all glucose and the overall reaction follows this expression where I have glucose plus 6 oxygens will give me 6 CO2s and 6 waters. And the enthalpy of this reaction is basically the enthalpy of this reaction is right here, and it's 2816 kilojoules. Okay, so he consumes 6,000 kilojoules, and we assume all of this food is glucose, so the 6,000 kilojoules undergo this reaction with this enthalpy. And so what are we looking for? Based on the above data, what is the metabolic rate for a human being in terms of oxygen used per meter cubed per person per second? So I want to get the reaction rate. So I'm looking for minus R for a human being in terms of oxygen, so it's minus RO2. In terms of oxygen used per meter cubed of person per second. So I want moles of oxygen used per meter cubed person per second, right? So this will basically be 1 over V person multiplied by D, or actually let me try to clean this up here. Okay. So this will be, where is the thing? Here we go. So I have my reaction rate in terms of O2. This will be, we said it's moles of oxygen per meter cubed of person per second. So this will be 1 over V person multiplied by D and of oxygen per dt. Okay, so we're looking for this expression basically. So in order to find the value of RO2, I need to calculate 3 main parameters: the volume of the person and the change of number of moles per time. Okay, so let's take them one by one. Let's start with the volume of a person. So we know the mass given is 75 kilograms right here, right? So in order to get the volume, we need some sort of density, hopefully you guys remember this. what is it? M equals rho V, right? This is kilogram per meter cubed, right? So basically, V is equal to M over rho. I know M is 75 kilograms, and the density, what's the density of a human being, right? Can assume that a human is just mostly water, right? Or mostly water, divided by kilograms per meter cubed. And here you have the volume of a human being, which was 75 kilograms, is 0.075 meter cubed. Okay, so this is all written on the slide here. So we're looking for RO2, which is minus 1 over V multiplied by dN by dt. So we're looking for the reaction rate in terms of moles of oxygen per meter cubed per second. We're going to start tackling these one by one. First one is volume. So assume the human density is equal to that of water, is just 1,000 kilograms per meter cubed. And from here, once we know, we assume the density, we know the weight of the person or the mass, can get the volume of one person. Okay, so this guy is done. So now we need to look at this parameter. So in order to get this, we need to see what type of information are we given. So I'm given that he consumes 6,000 kilojoules of food per day, right? So if I go down here, try and write it. So he's consuming kilojoules of glucose per 1 day, right? And then the reaction rate, you're also given a reaction rate, which is what? Which is 2816 kilojoules per basically 1 mole of glucose, right? Per 1 mole of glucose. So I can use these two pieces of information to get the moles of the change in number of moles of glucose per day. So if I divide this value by this value, I should get the change in number of moles of glucose per day. So let's have a look here. So you're told that 1 mole of glucose reacts with 6 moles of oxygen and releases 2816 kilojoules of energy, right? And this is basically the enthalpy of your reaction, which was written up there, which is 2816 kilojoules per 1 mole of glucose, right? And then you're also given that he consumes 6,000 kilojoules per day. And I want to basically convert these two elements into a form which will give me moles of oxygen per second, right? So first step is I need to change this into a form which will give me moles of glucose per day, and then I'm going to convert the glucose to oxygen and then convert the days to second. And this is what's shown on this slide. So I have 6,000 kilojoules per day divided by 2816 kilojoules per mole of glucose. So these two cancel, and you basically get, so this number here will give you mole of glucose per day, right? Moles of glucose per day. After this, I multiply this by the stoichiometric ratio between glucose and oxygen. So I have 1 mole of glucose to 6 moles of oxygen right here, and I get my final number, which is moles of oxygen per day. I then convert this from day second right here, and then I multiply this by the volume of the human being right here to get the reaction rate. Okay, so this is a simple problem, just go over it. Just a simple sort of motivating introductory problem for this course. Okay, and as you can see, the number we get here matches this figure where, you know, the human at rest. This is the reaction rate or metabolic reaction rate. is basically 0.002 moles of oxygen per second per meter cubed of human. Okay, so let's move on to talk about the main topic of this lecture, which is the kinetics of homogeneous single-phase reactions. And one thing to note is homogeneous refers to single phase, which means only gas, only liquid, or only solid. This is opposed to heterogeneous, which corresponds to a reaction which I have multiple phases, so I have gas and liquid, or solid and liquid, or gas and solid. So in this case, we're only talking about homogeneous reactions. So suppose you have a single phase reaction which follows this formula, AA plus BB with a reaction rate constant of K will give me RR plus SS. Okay. The reaction rate equation for this reaction will be minus RA is equal to minus 1 over V dNA by dt. And again, dNA by dt is the change of number of moles of A with time, and minus 1 over V is, 1 over V is volume, and the minus sign here is due to, and the minus sign here is because it is being consumed, right? So it's important to note that if I'm representing the reaction rate in terms of a component that's being consumed, I always have a minus sign, right? If I'm writing the reaction rate in terms of component that's being produced, I will always have a plus sign. Okay, so be careful of these signs when writing your expressions. And the units of the reaction rate of the rate equation is amount of A disappearing per volume per time, moles per meter cubed per second. Another very important thing to note is if you know the reaction rate of one component, you can get the reaction rates of all the other components, right? So if in this, using this type of relationship. So both my reactants right here, A and B, they both have negative signs, right? Or minus signs, and these are my products, R and S, and they have positive signs here. And they're related by the stoichiometric coefficients, right? So minus RA over A is equal to minus RB over B. And you can see A and B correspond to your stoichiometric coefficients in your elementary reaction expression here, or in your elementary reaction formula. Is equal to RR divided by R, and then RS divided by S, okay? So this expression here is very, very important. It's very common to lose track of this type of relationship between your reaction rates based on different components. And again, there's something to note, minus sign is for reactants, plus sign is for products. RA is an intensive measure, i.e. it's independent of system size. So it's a function of volume. So whether you're getting the reaction rate for a very small volume or a very large volume, the number itself is independent because it is per volume. This is in contrast to having extensive variables such as volume, mass, etc. So RA is intensive. You need to be aware of this. It's independent of your volume or of your mass of either reactor or catalyst. Okay, moving on. The reaction rate is influenced by two primary parameters, right? And we know this based on a lot of experiments, a lot of experience, so it's just known to be a fact. The two parameters are composition and energy of the reactants. And by composition, I mean the concentrations. And I'm sure you've seen all of this before from a basic chemistry course where, reaction rate is a function of concentrations, Ca to the power A or Cb to the power B, whatever, and the energy of the reactants, which is primarily your temperature, right? Or energy could also be like light, radiation, or any other type of energy, but most of the time it refers to temperature. Therefore, your reaction rate is a function of temperature-dependent terms and concentration-dependent terms. And it's usually represented using this, so if I'm looking at the previous reaction, or the reaction on the previous slide, minus RA is equal to K, my reaction rate multiplied by the concentration of A to the power of A, which is the stoichiometric coefficient, right? So if you remember, AA plus BB is equal to RR plus SS. And your reaction rate constant can also be represented in this form, where I have a pre-exponential factor multiplied by the exponential to the minus E over RT, where E is your activation energy, joules per mole, R is your ideal gas constant, and T is the temperature, right? E over RT again is dimensionless, so if you want to just check your units or whatever, you just realize this. And let me write it here explicitly, so just if anyone needs to remember this or be reminded of this. K is equal to K naught E to the minus E over RT, right? This is your pre-exponential factor, activation energy right here, ideal gas constant, temperature. Okay, moving on to defining other terms. For an nth order reaction, the rate constant has the following units. So this is your general guideline to determining the units of any reaction. So if I have a first order reaction, the rate constant has units of 1 over time, because it's time to the minus 1 multiplied by concentration to the 1 minus n, where n is the reaction order. So if it's first order, this goes to 0, 1 over second, for example. If it's a second order reaction, it becomes 1 over second per concentration, which is usually mole per meter cubed, whatever it is. This is the equation you're going to use, or this is the formula you're going to use to determine the units of your reaction rate constant. And another thing to keep note of, this line right here, just when doing your calculations, K naught is a very big number, and E is a very small number, right? So if you're doing your calculations and you don't see this, your calculations are wrong. You need to revisit them. Okay, moving on. When you have a single reaction, so here we're going to talk about single reactions and multiple reactions. So in the case of a single reaction, product distribution is fixed by stoichiometry, right? So by this, what I mean is, if I have A plus B goes to C. So for every A moles of A, I'm going to get, and B moles of B, I'm going to get C moles of C. My product distribution is always controlled by my stoichiometry in the case of single reactions, right? For the case of multiple reactions, it can be much more complex because you can have multiple reactions in series, for example. So in the case of monochlorination of benzene, followed by dichlorination. So if I have a benzene ring right here, I do this, I get a benzene with a Cl2. I do a second step, get a benzene ring with a Cl2 here, and then maybe a second Cl2 here. And this happens in series. And in this case, the product distribution, how much of this guy do I have versus this guy, depends on many factors, and it's not as straightforward as looking at the stoichiometry. In this case, you need to get the differential equations, look at the temperature, look at this and that, and determine your concentrations as a function of whether reactor volume or time. Multiple reactions can also occur in parallel. So for example, I could get, so in this step, for example, I could get dichlorination could be 1,3 or 1,4, right? So basically what this means, if I have a benzene right here, Cl2 plus a Cl2 could go, for example, to 3 position, or it could be to go to a 4 position, it could go to a 5 position. Actually, it's not common, but it could happen. And I have a bunch of other products which all happen in parallel, right? And having reactions in parallel is not uncommon. You're going to see this. If you will see this a lot, if you end up working as a process technologist or as a process engineer or refinery or something like that. Okay. Alternatively, you could have much more complex schemes. So I could have A plus B going to R, and then R reacting back with B to give me a new component S, where I have both series and parallel reactions happening at the same time. So in this case, this above set of reactions is parallel with respect to A, sorry, series with respect to A, so A goes to B, and A plus B goes to R, and then R plus B goes to S. So from the perspective of A, this system is in series, but it's parallel with respect to B, because B reacts both with R and A to give me R and S as well. So this is a more complex system, where in this case, I really need to look at the fine details of the reaction rates of the reactor design, differential equations in terms of time, in terms of distance, all this stuff. And these are examples where this happens, chlorination of benzene is a complex one where you see all these types of things. But for the present and for the initial part of this course, we'll be only dealing with single reactions. So just realize that, right? So for the first part of the course, we won't see this. It's good to acknowledge that they exist, or have it at the back of your head, but we won't really deal with them until later in the semester. Okay, let's now go and define what an elementary reaction is. An elementary reaction, which is one in which your rate equation corresponds to your stoichiometry, right? So for example, if I have A plus B going to R, and my rate equation with respect to A is just K multiplied by CA multiplied by CB. So I see here that the rate equation corresponds to the stoichiometry. There is nothing strange going on here. So this is called an elementary reaction. So your rate equation corresponds to your stoichiometric equation, right? As opposed to a non-elementary reaction where there's no correspondence between the rate equation and the stoichiometry, right? So a very common one is formation of ammonia. So I have nitrogen plus hydrogen will give me ammonia. If you do this in the lab and you try to measure all your concentrations and try to plot your reaction rate constant, or try to, get your rate equation, you'll find out that's something completely different than what you see in your stoichiometric equation, right? So I have K1 and 2H2 1.5 minus this and that, very different, right? And so this is called a non-elementary reaction, and this is most of the time, or always actually, is due to the fact of having intermediates, having free radicals, and having other, chemical elements available in the reaction, right? Which we don't directly see, or we may not be able to detect. Common one is there's this new type of thing. We have a zip reactor, where you zip a molecule very quickly through a high temperature, low temperature, and you get a free radical, but the free radical is not there long enough for you to be able to detect it. So your reaction rate is very strange, but you can't really detect the intermediate to try and get a feasible stoichiometric expression for it. And this happens a lot because most of the time reaction rates are predicted by experiments. And we try to match the experiments with the stoichiometry, with this and that. Okay, so just recapping, elementary reaction is one in which your reaction rate is can be predicted using the stoichiometric expression. A non-elementary reaction is one in which your reaction rate here cannot be predicted using your stoichiometric expression. Okay, let's move on and define more terms. Molecularity. Molecularity only applies to elementary reaction, and molecularity is the number of molecules involved in the reaction. So usually one or two, or very occasionally three. So for example, if I have a reaction which is A goes to B, this has a molecularity of 2. If I have A plus B goes to C, this is a molecularity of 3, just the number of molecules involved in the reaction. Okay. The order of the reaction is also an important thing to know, because it will help you know your units, and then if your units are all set up properly, it's most of the time a good indication that you're solving correctly. So if a reaction involves chemicals A, B, and C, then minus RA minus RB is equal to K, CA to the power A, CB to the power B, CC to the power C. And this is obviously for an elementary reaction. For a non-elementary reaction, A, B, and C will not correspond to stoichiometric coefficients. But talking about elementary reactions, if you have a reaction involving 3 chemicals and this is your reaction rate, then the reaction is said to be of order A with respect to chemical A, order B with respect to chemical B, order C with respect to chemical C, etc. And your overall order of reaction is A plus B plus C. Okay? So in order to determine the reaction rate, you just add up your stoichiometric coefficients up here. Okay, going back to talking about elementary reactions, and this is just an important point for you to remember. If we say that the reaction is elementary and write A plus 2B going to 3S, so what does this mean? So depending on what element you're talking about. So I'm talking about the reaction rate with respect to A. It's going to be K1 A B squared, right? If I'm talking about the reaction with respect to B, again, it's going to be K1 AB squared, but because both A and B are reactants, I have a minus here. Talking about it with respect to C, then I have RC, the plus sign, is equal to K1A B squared, right? And what this slide is saying is that it cannot be all of these because, you know, the reaction rates cannot be the same because I have these stoichiometric coefficients here. So in order to avoid ambiguity, when a reaction involves different numbers of molecules, we must specify which component is being referred to when we specify a value for K, right? So what this is basically saying is, although A to B or 2A to B are both valid, only one of these can be correct if the reaction is elementary, right? So what this slide is saying basically is, you just need to keep an eye on what the chemistry actually is, right? So even though, or maybe in chemistry courses, you were tempted to just cancel out this and say one molecule of A goes to one molecule of B. Sometimes it might not be the case when dealing with larger molecules or more complex reactions. So you just have to keep an eye on what exactly reaction rate represents. And this involves taking a closer look at the experimental data you have, at the units you have, to try to avoid falling into this mistake. And it's not common, and I don't think we're going to deal with it this semester, but it's just something for you to know. Okay. So in the cases of you have a non-elementary reaction and you want to get at the kinetic description, so just going back to this, let's say you have a non-elementary reaction here and you want to get the kinetic description. So you have this type of reaction. I looked at my experimental data. I found out that they do not match the stoichiometry. So I need to find an expression. What steps should you use? These are your typical steps. There's a guessing step involved, and we're not going to deal with this semester. It's just for your knowledge. You need to postulate a mechanism, just come up with a mechanism. Assume that each step of the reaction involving intermediates is elementary. So, for example, if I have, so I can assume that, in this case, I can assume, so if I have A, I can assume that A goes to A star and this elementary reaction, then A star plus B goes to S star, this second elementary reaction, that type of thing. So I need to come up with a mechanism, come up with a theory, and then test it. And then if these intermediates have appreciable concentrations, then we could measure the concentrations. Otherwise, they can be very low. If they're very low, we assume that they're zero, and then we assume that the rate of change is zero, and then we go from there and derive a rate expression. Okay. So these are the steps you need to follow. It becomes clearer once we follow an example, once we do an example. So in this slide, we have a motivating example for this type of scenario. So for example, so this example looks at finding a mechanism for a non-elementary reaction, okay? So let's say I have a non-elementary reaction, A plus B going to AB, and I do it in the lab and I see the following observations. First of all, the reaction is irreversible. Second of all, the reaction rate is independent of A. Second and third of all, the reaction rate is proportional to B squared, okay? So you have this reaction, you do it in the lab, and you have this observation where irreversible, reaction rate is independent of A, reaction rate is proportional to B. So how do you define the mechanism? Again, you follow the steps we said here. We're going to postulate a mechanism and then make some assumptions about the reactions, cancel out some numbers, assume intermediates are equal to 0, and eventually get to the final result. So how do you explain this? So we propose a reaction. And this proposal step is usually the hardest step. So if you take a polymer chemistry course, for example, this is a very common type of thing. And however, most reactions will follow one of maybe 20 schemes. And with experience, you're able to catch it out quickly. But for this example, let's propose with the following reactions graph. 2B, and basically decompose this, gives me an intermediate called B2 star. And then B2 star reacts with A to give me B plus AB. Okay, so I propose this and I say these are the elementary reactions. This is the scheme which gives me this final overall reaction right here. And then I write the rate of formation of B2, right? So I'm going to say RB2 star is equal to K1 B squared because it's the rate of formation of B2, K1 multiplied by B power 2, minus the rate of consumption of B2, which is K2 multiplied by B2 star, minus the rate of consumption of B2 in this reaction, which is K3 multiplied by B2 star multiplied by A. So the rate of formation of B is equal to this, and I set this equal to 0 because it's an intermediate, and it basically, once it appears, disappears immediately. So the overall rate is 0 because I don't see any B2 star in the products, okay? And again, this follows the steps mentioned up on this slide where, we postulated a mechanism, we assume that each step is elementary, and then if these intermediates had an appreciable concentration, we would know that they are present and we can measure them. If they don't have any appreciable concentration, then they must be very low. So in our example, B2 star, it does not show up in the product. So we're going to say concentration is very low. So if you assume that the concentration is very low, that means that it's 0. And that means that the rate of change is 0. And this is what we did here, right? Propose the mechanism, said both reactions are elementary, wrote the rate of change in number of moles of B2 of my intermediate. I don't see any intermediate in the product here. So this means that this rate of change is equal to 0, okay? And once you get to this point, once you see this 0 right here, it gives you an opportunity to do some algebra, right? Because I can move some of these expressions to this side and get maybe concentration of A in terms of B2 star and all this stuff. And this is what we do here. So I basically factor out B2, move this guy to the other side, and then divide, and I get B2 star is equal to K1 B squared divided by K2 plus K3 multiplied by A. Okay, so now I have an expression for the concentration of B2 in terms of the components I see in my reaction, in terms of B and A. So what do I do with this expression? So I'm gonna basically calculate the rate of reaction or rate of formation of AB, which is my product here. So what's the rate of formation of AB in the scheme which I postulated or I proposed? the rate of formation of AB is governed by this equation. So RAB, where is it? There we go. RAB is actually equal to K3 multiplied by B2 star multiplied by A, right? So this is the reaction rate of AB, which is right here. K3 multiplied by B2 star multiplied by A. A, I see it in my reaction, B2 star is a hidden intermediate. However, I already derived an expression for B2 star right here. So I'm going to plug this expression into my reaction rate equation for AB. And when I do that, I get this form. So RAB is equal to K1, K3, B squared, multiplied by A, divided by K2 plus K3 multiplied by A. Okay? So this becomes my proposed reaction rate for the formation of AB. If K2 is equal to 0, or is much less than K3 multiplied by A, then RAB is equal to K1 B squared. So then you can say, K2 is equal to 0, and K2 is basically this reaction. And this is an assumption you can make really based on what you see in experiments, And if I assume that K2 is very low, so this cancels out, and then I have this expression, the A cancels with the A, K3 cancels with the K3, and I get an RAB, which is equal to K1 B squared, and this matches what I see in experiments, which is it's independent of A, and it's proportional to B squared. Okay? So when dealing with non-elementary actions, there is really, it's a trial and error really to get this scheme. Here the scheme was given, and all the math worked out in a very nice way. But realistically, if you're running an experiment and this is all you have, it will take you a bunch of tries until you get to the right answer. And then, of course, after you get this, you need to test it versus your experimental data, see if it makes sense. It might not make sense, and you have to find something else. Okay. So there were the predictions based on the proposed reaction scheme, consistent with the observation, and just exactly what we all said, or what I just said a few minutes ago, or just a few seconds ago. Okay. So this is just something for you to know. This will not be tested, but you might get a homework problem on it. But just to realize that dealing with a non-elementary reaction is a completely different animal than dealing with an elementary reaction. Okay, temperature dependence of the rate equation. So I'm assuming you've seen this before, maybe in thermal, maybe in some chemistry course. So consider reaction to different temperatures, T1 and T2. Assume that the activation energy does not change with temperature. So activation energy usually does not change with temperature. Then at the same concentration, ln R2 divided by R1 is equal to ln K2 divided by K1 is equal to E over R, 1 over T1 minus 1 over T2. Okay, so this is an equation which you should know and you should be able to use, and you should be able to derive as well. Or you should be able to derive as well, basically. The way we derive it is, we say K is equal to K naught E to the minus E divided by RT. So if I have two cases of this, or at two temperatures, so I have K1 is equal to K naught E to the minus E divided by RT1, and then K2 is equal to K naught E to the minus E divided by RT2. If I divide these two guys, that's shocking. Okay. Let's try to do this properly. Okay. So if I let's move it here. Actually, if I try to divide these two guys, I get K1 divided by K2 is equal to E minus E RT1 over E minus E RT2. And then, you take the ln of this. So if I take a ln here, ln K1 by K2 is equal to, um, so just before this, so this will be equal to what? Minus E over R T1 minus or plus E over R T2, right? Because exponentials, so this moves up here. So if I take ln here, the ln cancels with the E on this side, so I get minus E over R T1 plus E over R T2. And this basically becomes, if I take E over R out, so I get what? E over R minus 1 over T1 plus 1 over T2, right? And yeah, so in this case, let's look here, ln K1 over K2, right? And then if you flip them to get K2 over K1, this minus will flip to the other side, right? So if I flip them, so if I get K1, K2 over K1, and just in case you forgot this is equal to minus ln K2 over K1. And then if you want, you can move this minus sign to the other side and play with this expression. Okay, but know this expression, you're probably gonna get a few questions on it. And this is very basic. Okay, let me clean this up here. Okay, good. So let's have a look at a quick example here. Example, the pyrolysis of ethane proceeds with an activation energy of 300 kilojoules per mole. So in this case, you're given a problem right here where you're told that activation energy is equal to 300 kilojoules per mole. How much faster is this decomposition at 650 than at 500? So T1 is equal to 650 degrees Celsius and T2 is equal to 500 degrees Celsius. One very important thing to remember here is you need to always convert this to Kelvin, right? The temperatures here always have to be in absolute units. Okay, Celsius does not work, Fahrenheit does not work, and absolute units refers to either Kelvin or Rankine. Okay, if you solve this in Celsius, you're gonna get a very, very wrong answer. Solve this in Fahrenheit, you're gonna get the wrong answer. You need to convert it to Kelvin or Rankine. So solve this problem, you're basically, as you see here, you're given E, you're given T1, you're given T2. Convert them and you get the ratio of R2 divided by R1. And this is what we did here, ln, ratio of rates, activation energy divided by R, 1 over T, basically T1 minus T2 is equal to your rate of reactions. Okay, so yeah, just remember to always convert to Kelvin. This is a very common error. Okay, so this is the end of the first lecture, or the end of the lecture for this week. The homework will be posted, the reading material will be posted, and the homework solutions will be posted. Again, your homework will be due on next Tuesday, so please submit it by then. Again, you scan it or you take a picture and you upload it to Blackboard. I'm going to make the link available as well. Thank you very much.